Okay, so how large we can see that the massive structure, right? So people have been worked on it, and they have understood that even that we are talking about the large number of the antenna, but what people are telling that if 64 per sector, if we consider, then I think we can able to get the optimum performance. So that means 192 antenna at the per base station per site. Okay, so 192 antenna if you going to use, then you can going to get the optimum performance if you are going to use the massive MIMO. So this is one of the field experiment by the building the massive MIMO is done in the Lund University. Okay, say of the self hardware they are using the SDR. Okay, so SDR means normally they are, I think, use the USRP. Okay, and 6 SDR for the 12 user, 4 FPGA for processing, and a lot of cables. You see the massive MIMO looks like this. So maybe IIT Hyderabad also have designed one of the massive MIMO architecture, I think. Now, when you are going to the massive MIMO, right, it will going to consume a lot of energy consumption. So it is not only the hardware, that is also people are thinking that a lot of services also are going to use the energy consumption. Like you see that people are talking about 3GPP, we may have this consumption, but in the 4G, our energy consumption is decreasing. In the 5G, we are going to see that our energy consumption is reducing further. Now, when we are going to see that we are using in a particular device, we are going to use a different kind of applications, right? So maybe the WhatsApp, Instagram, Facebook, Google, YouTube, and others. So everything that consumes some of the energy. So you see that in the 3G, right, that energy consumption, the consume energy that the 3.9%, while the BS density is only 4 into 5 BS per kilometer. Like I'm telling that in 5G, it will be very dense network, right? So when it will be very dense network, how it is going to, you see, in the 3G, we will have a 4 to 5 base station per square kilometer. But you see, in case of the 5G, we are talking about 40 to 50 BS per kilometer square, right? So this is actually going to tell us about the energy efficiency. Now, when you are talking about the energy efficiency, how you are going to define that? So energy efficiency, I am telling that energy consumption is a cost, and the benefit I am talking about the data throughput. So if you increase the energy, right, your data throughput will increase, right? Now, how we are going to define, right, the benefit and cost ratio, bits per joule, right? So how many bits you can send per joule? So if you do the data throughput by the energy consumption, we can get that. Okay, with the coverage area, energy efficiency throughput, bits per second per kilometer square, joule per second per kilometer square. So if we go to the entire area, so when you're talking about the dense network, we can consider in that. And if you are talking about the heterogeneous network, right, which is a combine of all kind of network and how much energy they are going to consume, and at the same time, we want to see that how much data throughput they can give. So ratio between that, we can say that it is the energy efficiency. Or with the frequency, we can say that bits per joule per hertz. Okay, data throughput bits per second per hertz, and energy consumption joule per second. So it is like I'm telling that through the spectral efficiency. So this is a spectral efficiency. So spectral efficiency by the energy consumption, right? So if you see an example that 4G base station, right, data throughput is we're talking about the 28 Mbps, and in that energy consumption is the 1.35 kilowatt. So energy efficiency is the 20 kilobits per joule. Now, if you are talking of, then if it is that how we are going to enhance the energy efficiency and what approach you should take, And what the future is telling about this. If you can understand that energy consumption, if we increase the traffic load, energy consumption will slowly vary. At the same time, right, if you the traffic load, my energy efficiency, we need to increase. So that is what we need. I mean, even that if we want to increase the traffic load, my energy efficiency should increase. Now, if you see the three examples of the wireless communications, my data can increase, right? How, what is the possibility, different possible way I increase the energy efficiency? What is the first way? Data can increase, energy consumption decrease. My energy efficiency can increase. Data can decrease, energy consumption can also decrease. But rate of decreasing of the energy consumption is high than the rate of data. Still that way, I can increase the energy efficiency. What is the next way? Next way is the next approach is that data communications. Okay, so data communication can decrease. Sorry, 1 second. Data consumption, data throughput can increase, energy consumption can also increase, but the rate for the data throughput should be more than the rate at which the energy consumption will increase. Okay, so this is the way that we can see. So three different ways. Now, which one is the better, or which one will be happening for the future network? So people are seeing that so we need to have a trade-off between the data and most likely solution for the future network where we can consume the more energy, but energy efficiency will increase. So this will be the scenario for the future network, that we can increase the energy efficiency and energy consumption, but data rate will increase faster than the rate of the energy consumption. So in that way, we can actually require a trade-off between the, you see, this is the data throughput, we can do the Shannon formula, and energy consumption is the amplifier amplification and the circuit power consumption. So this equation can tell you that what kind of trade-off we are going to use. So there's a different metric are there which we can use, right? In the component level, antenna, power amplifier, baseband, equipment level, what device, what processor, because you know that you can purchase the different kind of mobiles, right? One particular mobiles can you can recharge in a day, once in a day, and some maybe you have to carry with the power bank. Okay, so the energy distribution will be more, right? Maybe what kind of coverage, what is the brightness you are going to use, what is the capacity you are going to use, what is the deployment, you are using only the voice call, or maybe always a video call, or maybe you are using a different kind of services which require a very high power, right? Or these kind of things that tells about that are having the impact on the energy consumption. Then come to the cyber physical system. Now people are talking about that industry 4.0, right? What they are telling that we have a three different things, that we have a information available. Now how to use that information, right? So there are three different things. Either you have a control, computing, and the communications, right? So you have informations. Now how to use that informations, okay? And so that you can do like monitored, coordinated, and the control and integrated by the computing and the communication core. So how efficiently you are going to use, okay, that information for improving the performance of the system, either maybe communication or maybe device or maybe entire communication infrastructure. Okay, so that is what people are talking about, the industry 4.0. So industry 4.0, right? We have autonomous robot. Okay, we have a horizontal and vertical integrations. We have a industrial IoT, we have a additive manufacturing, cyber security, augmented reality, big data. Okay, all kind of things are there. Now, if you are going to use this and if you want to control, right? So you need to have a information. Now that information you need to process first, right? So all these things, this communication, that you should get the information, you should control, right? All kind of things, you need to have a very higher capacity and higher energy efficiency. Not only that, if you are going for the beyond, people are talking about that virtual reality, okay, teleportation, right, holographic way, right, near to space, high precision service, okay, industrial revolution 4.0, autonomous V2X, all kind of things if you are going to do, right, then we need to have a different kind of, like you're telling that terahertz level data, okay, extreme focus and short range communications, AI in the network, extremely high radio density. So all these things, very high network heterogeneity, right? All kind of things that people can support. There's a different, people have proposed a different kind of things. Now, one of the important things that, so these things is telling us about that I am the communications technology is moving towards the supporting or going to move towards the end of the Shannon capacity, right? So can we reach the Shannon capacity limit? So Shannon capacity limit is, you are going to see that only that these things are going to change. So how we can exploit this the channel matrix, right? Because our age is still random and uncontrolled. That is, I cannot control, but I can only exploit. So how can we make age is arbitrarily large, right? If age is large, right, it tends to 1, then I can say that it is controlled dependent by the P. So P is our control. How can we make the AS is less random for Rayleigh fading to the Rician fading? Okay, if it is a less random, Rayleigh fading means we don't have Rayleigh fading is, it is non-line of sight. Rician fading is the line of sight. So the moment we have a line of sight, we will have a control. So existing technology, beamforming, power control, adaptive modulations, which is a link adaptation, only adapt to age, but they don't have a control over it, right? Now, how to break the ultimate barrier, achieving the ultra high capacity or ultra high reliability? The one of the promising thing is the smart and reconfigurable wireless environment, right? That is, we are talking about the intelligent reflecting surface, right? We can control, right? So this is the architecture of the intelligent reflecting surface. So this is the reflection, right? It will be reflected from the any signal coming from the base station and reflect accordingly as per the user. Okay, so they have a one copper backbone and the control circuit backbone, which is controlled by this RIS controller. Okay, so this is a digitally controlled meta surface with a massive low-cost passive reflecting surface, right? So this is things that we can reconfigure. This can provide the reconfigure the properties like tuning impedance, length of the delay lines, or the phase shifter. Okay, because they have to form the beamforming, and they can only steering the beams by changing the reflector. The reflector can be changed by using the maybe different kind of phase shifter or the delay. It can be intelligence by the real-time programmable and the controllable, and it is a two-dimensional array of the scatterer. So that's why sometimes it's tell also that, and it will be controlled by all these things by the one RIS controller. And it sometimes tells also the reconfigurable intelligent surface, large intelligent surface, software control meta surfaces, all these things, it have a different name. So if you see the literature, you can see that they have been introduced by the different name. Okay, but functionalities all are same. Now, advantage that this is the easy to deploy. Okay, IRS is nearly passive device. Okay, so made of the electromagnetic material, and ERS can be deployed in the several structure. Okay, it will be environmental friendly, capable of the shaping the incoming signal by controlling the phase shift of each reflecting element instead of employing power amplifier. Normally in a communication we have a power amplifier, right? But it is not doing this. So that's why it is that not using any power, right? It is not an active device, it's a passive device. Whereas that massive MIMO, we see it's a active device. Spectral efficiency enhancement, okay, is capable to reconfigurable the wireless propagation environment by compensating the power loss over the larger distance. It can also due to the intelligent deployment and design, the software-defined wireless network may be constructed, which in turns provide the potential enhancement of the received signal to noise ratio. Okay, we'll see here that there are different kind of IRS, waveguide IRS, refracting and the reflecting. Normally, we use the reflecting IRS, right? That which is the here that we use the varactor diode using the tunable biasing voltage. Okay, and it will be pre-designed and the several digital biasing voltage level. We'll see that how it will actually work, right? It do the EM reflection. Now when it do the EM reflection, it will be use a biasing and using the, this is the element, right? PN diode is going to use EM characteristic of the BS as the phase discontinuity can be reconfigured by the tuning the surface impedance. The choice of the material of the IRS into semiconductor or the graphene, we can use that. When the pin diode is turned off, the incoming energy penetrates the surface. It's mostly absorbed. However, when it is on, the more incoming energy will be reflected. So that is what the control, right? So by using the diode on and off, we can see that this will be reflected or not. So varactor tune resonator are also used for the controlling the signal propagation. So this is the bias voltage can also do the phase shift, because phase shift is one of the important thing that which can tells about the if you remember the how the beam forming has how the beam form, right, how the beam forming work, that if you have an antenna array, there will be a phase difference among the all antenna array. So this phase difference is actually can help us to the steering the beam or the forming the beam, right, in which direction that beam will form, right. That is the main thing, that we need the phase shift of the incoming signal. The controller network records the running state and the receive the infrastructure. So you see, this is what that we have the reflector unit which can actually control the phase shift, and so that it can steering the beam accordingly. So this is one of the IRS implementations, right? So you see that IRS implementation, it looks like this. Okay, so this is the one university has been. I forgot the name of the university, but if you can see this paper, you can see the university name. So this is the structure, that what kind of character, what kind of capacitance, what kind of resistance, okay, they have consider that when they have designed the IRS element. Now this IRS, now the main thing is that how the signal propagates, right? If you remember the wireless communication, there is a one method, that two-ray model. Normally, the simplest way to calculate the received SNR, received power at the receiver side, and the two-ray model is one of the basic model into that. The IRS is actually working in that. Like this is the IRS, and the signal is, this is the IRS. The signal is coming from here. Okay, so signal is coming from here and reflected going back to the Y. So X is, I can say from the X, signal is coming, reflected and going, right? So this is, I'm doing that, and at the same time that signal may come from here, right? So I can say that this is a reflector, this is the point of reflector in this case, right? So if I can replace this one by this, the propagation model is almost similar to the two-ray model. Only thing that little bit, only thing that adding some other things. Okay. So this we are going to get this. Now, when you are going to see that what is the okay, so what is the things are there? Yeah, session will be end. I think 11:30 is the time, right? This session. Okay. Okay, so why is that? We'll have a DN, right? One HN from this point to this channel, and the another channel is this channel. So that's why you see here that H naught, that complex channel coefficient, right? When you are going to the HN, and this is the complex reflection coefficient when you are going to that. So when the signal reflect incident on the IRS, then they will have a one reflection coefficient. It will be it will be reflected by the reflector, right? So this is the two channels. So the signal received by X or received at the Y. So it is one channel, and this is the two channels. Now this channel, the second channel, reflector channel, will have a reflection coefficient, right? So this is sometimes we discuss, we consider that is the product and distance path loss. Hn is depend on the d1n to the power alpha 1. This is the path loss factors, and again this is the path loss factor, path loss exponent alpha 2. This is the gain by this d2n, right? So we have a two types of the things. So Hn is the the channel characterized channel gain for X2 reflector, and the Gn is the from reflect IRS to the Y. So again, we can say that this is a product distance path loss, right? We can say that it is a product distance or the sum of the distance. This is the same way we can say the sum distance path loss we can express like this. So this is the way we can see. Now, if you see the real propagation, how it is going to happen, right? How it will be different from the conventional propagation to the IRS-based propagations. So these are two things, that it will be uncontrolled propagation, right? We don't have any control on the channel. But if we are going to see the IRS, this is the uncontrolled propagation is there. But if we are using the IRS, we can have a control that what delay, what delay we can introduce, what phase we are going to introduce, that can be entirely controlled by the IRS. So one way we cannot have a control, and another way we will have a full control, right? So two different ways. That's why that IRS, we can say that we can control our age. We can use path loss exponent at alpha. Yes, it's not, it is just a notation, right? We can have a alpha, or some book you can use the n. Okay, so different book you are going to follow different book, different notation they have used. Is the reflection behavior of the IRS sensitive to the signal bandwidth? Maybe, right? Okay, so I'm not sure that it is sensitive to the signal bandwidth or not. See, phase is not on that. Phase is that working on the signal direction. Okay, so bandwidth may not have that much impact, but maybe if you are going to the higher bandwidth, it may have effect. But in normally when we form the beam, okay, in the beam forming, the bandwidth does not have any impact. But in case of the IRS, I'm not sure. Okay, maybe you have to look. Okay, most of the paper I have seen that while calculating any parameter, they are using Mijot G function or the Fox size function. Okay, I think little bit more maybe explain in the subsequent session. Okay, so just wait for those sessions. Maybe you can get the answer. Will the character works is terahertz? I think so far this IRS they are going to use in the terahertz band. It works. Okay. Any alternative? So far, people are using the alternative. Like you see, people are nowadays using the different material, right? Maybe the approach is same, but maybe different different material, right? Either people are using the graphene nowadays, so maybe slowly they are going to uh, they are going to use a optical material. They may be using in the later stage, maybe optical material in that sense. How many number of parallel beam can be formed with a 4 RF chain? See, normally that every RF chain will going to form a particular beam, right? So ideally, it's a 4 RF chain means you have a 4 beam, right? But advanced technology, sometimes that using the P-coding, during the orthogonal P-coding, they can increase. But ideally, if you are not using the orthogonal P coding, 4 RF chain means it will be using the 4 beam format. But by using the orthogonal P coding, you can increase. Okay, so continue in that our discussion here. Like we are telling that we are going to control by the phase shift. Okay. So ease of the end scattering element to the IRS, right? We can have a the transmitted signal and the propagate to across the LTI channel, right? So if it is a frequency response, we can get that it will be radiated and N it will be filtered by inside the N, then re-radiated again. And it is a passive electric circuit. So if you consider all these things and if you consider this figure, so you see this figure and we finally we have, right, different kind of you see channel to element, okay, different kind of response we have. So finally we'll get our H, because our H need to be controlled. So our H we are going to get, this is the convolution of the all impulse response, right? Either B, nu, and the A. So finally, YBT, which is received by the at the receiver, it will be this channel response convolved with the X. Right? That is the typical equations, right? When we go into the get the signal from the X and the channel response, so H and X will be the convolution. Now here H is total this, and they are also convolved to each other, right? Channel to element, channel to response, and the element channel to the element. So these all are all together as consisting a total channel, so which we can control using the IRS. Okay. Yeah, you can use the MEMS, but this MEMS is very costly. Okay. So where that when you are going to the IRS, okay, it's a very cheap solutions people are talking about. So MEMS it will be very costly equipment. Normally MEMS we are going to use in the optical communications, right? Which is the 3D MEMS. Okay. So which will require very high precision. But that here that we have only one control, the phase shift, which is not which is very less costly and passive device. Whereas the MEMS it need to be activated. Now IRS is a multipath. If you are going to see that all kind of the impulse response we can do, right? That A, right, we have a propagation and a delay, right? So all kind of thing delay path can be accommodated, and we can get a discrete. So this is the propagation laws of if you are going to consider that different N, LA and LB path. We have a different kind of path. Okay, so we will have a TX to RS. So due to product operation, each path is very weak. Okay, but large number of paths can be potentially lead to a good SNR. So this can help us, help the communication using the IRS can increase the high SNR. Each path also associated with the phase shift and containing the accumulated delay. The sync function determined determined how the signal energy carried the path divided between the M taps of the FIR filter. Now, how this IRS can be used? Right, you see that we can use this IRS for the coverage extension. You see that if there is any block, the signal can be reached by reflection of the IRS. Another thing, that improving the channel rank condition. Right, if you don't have a IRS, we will not have this path. Only one path will be there. But having the IRS, I can get a 3 copies of the same signal. So my channel rank will increase. At the same time, right, we can have a refining the channel statistics, right? So maybe from direct we may have, right, from the direct we may have LOS, non-LOS signal, but from that we can have a LOS. So that's what I'm telling, that if it is maybe that NLOS signal, like non-line of sight, but using this IRS, we can have get a one LOS signal, right? So this is I can say it is a LOS signal. So my entire standard statistics was the LF fading earlier, but now we are going to make into the Rician fading. At the same time, we can do the suppressing, right? By using this IRS, we can do the interference suppression also. So very different way we can use the IRS for the different applications. So this is you can see if you are going to implement IRS, you can implement IRS in everywhere, right? Maybe in the office, in the roof, okay, in the side wall, and everywhere you can put the IRS, you can use. Either in a satellite also, you can use the IRS. Because see, the moment you are moving from the Rayleigh fading scenario to the Rician fading, you will have a line of sight. The moment you will have a line of sight, I think you can get the good signal. Your SNR will increase, your capacity will increase. So advantage of the IRS, right? We can see that if we have a DF relay or the IRS, right? You see the IRS, my signal energy efficiency is much more than the CISO, and in some cases, right, it is also increased, right? Transmit power in case also it will be decreased, that if you are going to use the more number of IRS. Okay, so this is giving an idea that how the IRS is advantageous for the wireless communication system, where that it can support the higher capacity. At the same time, it is going to support the increase the energy efficiency also, if you are going to use the high number of the element. I see that if we are going to use the same rate, right? So this is the IRS and this is the DF. Okay. Now for that so we have a SNR gap. To improve this SNR gap, we need a large surface. It is giving an example that why we need the larger surface when we need the meta surface IRS. What is the requirement? Because we need to get a very high SNR advantage. Then see the channel, right? If you like, we already discussed that channel. If we have this, right, we can get from this to that and this to this. Then we have a 3 component. That one is the IRS component, source to IRS, IRS to receiver, and one is the direct link. So if you are going into that, we see that the channel model will take about This is the LOS model, and this is also NLOS model, which is going to the, maybe this is the scattering, okay, but and the direct link also we are going to that. So at the receiver we are going to get all, right? So this is going to affect the phase shift. So when we are going to the phase shift, so phase shift has a the continuous phase shift we are going to get, right? So it may be from the this is the epsilon, that for convenience we return that the epsilon m. So if you have a number of elements, we can get that. Okay, so it is also desirable to obtain the additional phase shift at the direction other than the targeted one, right? So as a result, that we can say that meaning of the number of multipath component are sufficiently large, then these two component, okay, are exhibit complex Gaussian distribution with the zero mean. Okay, so this is a central limit theorem, right? If you have a more number of things and if nobody is actually dominating, then we can consider entire response is the Gaussian distribution, right? In deterministic, that provides a non-zero mean. So if you go for the SISU system, we'll have a passive beamforming, right? This is the SNR. Okay, you can use this SNR to get the maximize the rate, okay, which can give by the using the SNR maximization. So this is the figure. You see that if we have a free space and the distance fading, then we can actually get this, right? And you see that from this to this, we can get the gain, that if we gain the doubling the n. So if we are using the number of n, increasing the number of n, number of element, you see this is a 200 element and this is a 400 element. So every 400 element, every doubling the n, in case of the IRS, I can increase the two spectral efficiency increased by the 2 bits. That's a huge. Then again, that if you are going to do the power scaling, right? So power scaling again is telling that if we are using the sufficiently large n, then we can see that it will be increased the quantitatively here. You see that PR is equal to n square, right? So that is what the entire thing, right? If you have a pathless model, it is exactly doing in the same way, right? So if pathless model, both AP IRS and IRS user link is said to be this, okay? D naught is the link distance, okay? And this is a different kind of, this is the pathless component, that 2.4 and 2.8, which define the free space and the decision and the relativity. Then if you see the SIMO system, MISO system, right, it is exactly also giving the performance, okay? You see that if we have this, that IRS, okay, the MRT with the IRS, so MRT is with the maximal ratio transmitter, okay? So this is this value. So without this and with this, we can see the AOE is the better performance. So this demonstrates the joint active and the passive beamforming design is essential to the optimum balance between the transmission towards the user directly and that via IRS reflection to maximize and the receive signal power at the user. So I'm just showing that, giving an idea that how the different combinations, like in the SISO system, it is also having advantage. MISO system, it is also having advantage. Even if you are going to see in case of the MIMO system, it is also going to having the advantage. Okay, so the achievable rate, you see, it's increasing that without IRS and in a random phase. That so achievable rate, you see that from this is the 25. How much it's a difference? So maybe 2 bits per second, 2 bps almost 1.5. So 1.5 bits per hertz is increasing. So that means it's a huge, right? If you are going to use a 100 megahertz that, then maybe it will be into the maybe 10 Mbps more. So that is the way that if you are going the IRS, right? If you see here that they are using for enhancing the spectrum sharing, it can also, the IRS can also support this. You see, this is my signal transmission. This is a reflector. Okay, so it may from here you see this is the one transmitter. This is another transmitter. So by default they may do the interference, but within the reflector I can see that, you see, this is using only this type and this is using in this side. So I can, there is no interference, okay, RB by the respective receiver, and reflector can control, because reflector can control, I can control that this element can only reflect, right? So because I can this RIS controller can control the phase shift and the passive reflector. So the moment we can control the age. So there will be no interference. Okay, so we can cancel the interference in that. In another way also we can see that the multiple receiver enhance the system capacity. Multiple signal antenna device distributed the 3D space transmit in the vertical plane in the meta surface. You see, they are using the the IRS in such a way that the capacity will be increased. And you see the different combinations here. I'm showing the different combinations of the uses of the application of the RIS. You see the RIS is secured communication using the Fanley jammer, right? This is transmit beamforming. We have reflecting surface. Okay, then we can have a RIS controller. We can, so even that this jammer can jamming this beamforming, right? But it does not going to. So this is, so we can use this. So it is a secure communication system with friendly jammer. So jammer also we can control. Okay, this is a CISO downlink, like I told. This is the MU downlink. How we are going to use? Maybe that we are going to use that multi-group, multicast downlink communications. See, what I'm trying to say is here that the way the massive MIMO, right? We are forming a clustering, then grouping, then communications. Here is exactly doing in the same way, right? So the IR is also having the similar capability, but with some other advantages, right? So with this, I think just I end of the session. If you have any questions, yeah, I think you have one question is there. In case of the coverage extension, do the signal coming from the BOS, NOLs and the IRS LOS add to the user end? See, it can come from the BOS as a NOL, because even that you are blocking the direct view, but they just medium can be a scattering medium, right? So they can come. LOS signal come to the user, right? You cannot block it, right? So always there will be LOS signal, and IRS is the going to the LOS. As always there will be an non-line of sight signal, but for the LOS signal you are you are using IRS to provide the LOS signal. So user end will definitely going to signal. Yeah, do the both signal add? Yes. Okay, so elaborate on the IRS assisted secure communication. Yeah. See, like I'm telling that you can have a jammer, right? So the moment you will have a jammer, right? So it can actually, jammer is what? That it will be blocking your communications, right? So the moment jammer is blocking your communications, but if you want to communicate, right, you can communicate using your reflector, because IRS has the permission to read the interference cancellations that you can be used. Pin diode should be on the when IRS is reflect. It means it takes the energy when how to would be the passive element. Yeah, it's a good question. See, Now, diode can be on in a different way, right? Right. It is not that only you have to give the power, then only it will be on, right? How you are going to design your diode, like that's what I'm telling, that you can have a different kind of meta surfaces, right? How to do the diode. So it is not always equal the power. Okay, so what is the minimum sensitivity of the RX system of the IRS system? See, minimum sensitivity of the communication system, if you're talking about the sensitivity, what is the, that is sometimes it always depends on the what is the minimum SNR requirement for the communications. Suppose if you are going to use a you are using the BPSK modulation and the voice communication, so maybe you can use the maybe 10 Mbps, sorry, 10 dB SNR is good. But if you are going to use the video communication, maybe you require 20 dB SNR. So it depends on the what service you are going to use. Okay, what modulation you are going to use. Okay, it depends on that, right? So sensitivity, see, sensitivity, it depends on that. Sensitivity, normally we are talking about the when you are going to having the on a sensor, right? How it will be worked. It should not be sensitive. The device should not be too much sensitive, so that it will not consider, it will consider noise as a signal. Okay, so it should not be too much insensitive. Even that very weak signal also it will consider as a noise, right? So it depends on how you are going to design the system. Okay, why India has been unsuccessful in providing high quality internet service despite of so much manpower and technology environments? See, I think that's a question I cannot answer, right? Because it's a policy of the government, right? So maybe because of that. Can you please comment on the phase factor introduced using CISO and the MIMO and see, phase is introduced by the IRS, right? So and if the phase is introduced by steering the beam, right? So if you can understand that how beam can be formed by using the antenna array, so they are defining by the different phase component, and you can actually steer the beam. So it is nothing wrong, nothing there with the CISO and MIMO, right? So phase is on the element. If you are controlling the delay of each an element, and that is in turn controlling the phase of the between the element. That element will tell about the how you are going to forming the beam and the steering the beam. So it is nothing but the CISO and MIMO. MIMO is just a antenna receiver. Can we expect Rician fading? Yeah, we are making so IRS is for that only, that from relay fading to the relay fading. Sorry, relay fading to the Rician fading. From the non-line of sight communication to the line of sight communications. Our mobile is communicate in the designed to communicate in the non-line of sight. But for IRS, we are trying to going to provide the LOS component so that your capacity SNR can increase your then the capacity is going to increase. Okay, where can find the RIS in an outdoor environment? Okay, yeah, I think subsequently you'll get a lot of answers, right? It will be answered in the next session, like Priyanka madam already told. Yeah. In that case, IIS modulation scheme will be limited. To overcome, we have increased the transmit power. No, it's not a limited, right? See, MIMO system, I think it is a continuation of the MIMO system. No, I think, Arvind, I think I just lost your questions. Okay. The continuation of the question, IRS modulation scheme will be limited. To overcome, we have to increase the transmit power. See, if you have a, I think I understand. If you have a LOS component, okay, so obviously your SNR is going to increase. So the moment you have a high SNR system, then definitely you are going to use the higher modulations. The moment you have a higher modulations, your capacity will increase. Obviously, you are telling that your energy will system will increase. But if you remember my discussion on the how you are going to calculate the energy efficiency, if rate of increase of the capacity will be high, then definitely energy consumption, energy efficiency will increase. In what rate data is data rate increase, and in what rate energy consumption increase. If the data rate increase, rate of the increase of data rate is higher than the rate of increase of energy consumption, your energy consumption, energy efficiency will increase. Okay, so don't be confused that energy consumption increase and energy efficiency increase, both are not same. You may have the high energy consumption, but but at the same time, the energy efficiency can be reduced. So don't be confused in the two things. Increasing energy consumption and increasing energy efficiency are the two different things. Two are not the same thing, because energy efficiency is related to the data throughput, while the energy consumption is only are not related to the data throughput. It is related to the energy consumption of the hardware or the transmit power. See, in the LOS, using the IRS, using the LOS, we are not increasing the transmit power. We are increasing the received power by providing a LOS component. Not that we are increasing the transmitting power. Transmit power is same. But providing a LOS, I am giving an alternate path which is supporting the LOS. Because of that, my receive power is increasing. So I am not without IRS, my SNR may be 10 dB, but with IRS, my SNR will be the 20 dB, where that all other conditions are same. I'm giving a typical example like this way. So we are not consuming any energy because the IRS consume very less power. Okay, I think yeah, many more questions in the subsequent session will be answered. Okay, so thank you everyone. I think we are closing these sessions. Maybe we are moving to the next session. Thank you everyone.